Hello everyone and welcome back to the video lecture series for Calculus 1. Today we are going to be starting with an introduction to derivatives. So before we get into derivatives, we actually need to do a little brief history of the development of calculus, because the historical context for the development of calculus is actually extremely important for derivatives, especially in the notation that we use for derivatives. So calculus was not, quote, invented by one specific person. It was developed over a very long span of time by a large group of people. So the development of calculus is popularly credited to the mathematician Sir Isaac Newton and Gottfried Leibniz. So the roots of calculus really go back to ancient Greece, to Archimedes, and it was a slow developmental process over time, but we really attribute the development of calculus as we know it today to Sir Isaac Newton and another mathematician called Gottfried Leibniz. Everybody's heard of Sir Isaac Newton, but not a whole lot of people have heard of Leibniz. Now, these two individuals developed calculus simultaneously and independently of each other in different parts of the world. There was a whole controversy about it because Sir Isaac Newton was basically a celebrity and Gottfried Leibniz was not, and Newton was British and Leibniz was not. So there was like a whole controversy about it where Newton was accusing Leibniz of stealing from him, and it was a whole huge mess. Fascinating stuff. But anyway, as we know today that they developed calculus simultaneously in different parts of the world. So because they developed calculus independently, they developed their own notations that were independent from each other. And each of their notations have their own similarities and differences, which is why we use them, and they both have their advantages and their disadvantages, which is why we really use both. Now, much later, another mathematician named Cauchy then rigorized it and kind of put it all together to resemble the calculus that we know today. So, also, because of calculus's roots in ancient Greece, that is why tangents of circles and tangent lines, that's why they share the same name. And secants of circles and secant lines is why they share the same name, because it does have its roots in geometry back with Archimedes. So just to recap from the last few videos, with average rate of change, remember the average rate of change of a function is equal to the slope of the secant line between the endpoints. A secant line on a curve is a straight line that connects two distinct points on that curve. So the average rate of change of a function on a closed interval a to b is equal to the slope of the secant line that connects the endpoints a, f of a and b, f of b. And the average rate of change formula, which is really the slope formula, is given by f of b minus f of a over b minus a. So this is just a visual of what a secant line is. It connects two distinct points on a curve. And instead of using a separate letter b to indicate the other endpoint, we can call one endpoint a, f of a, and the other endpoint we can call a plus h, where h is just some arbitrary distance away from a, and then its y-coordinate is going to be f of a plus h. So a tangent line, as we have covered in a previous video, is a line that touches a function's graph at exactly one point. So while a secant line connects two distinct points on a graph, a tangent line touches the graph at exactly one point. And that point is called the point of tangency. So here are just another couple of visuals of tangent lines. So this tangent line here touches this graph at approximately this point here. And you'll notice that the slope of this tangent line is negative. And if you take a look at the original function, which is this parabola-looking thing, on this interval, especially at this point right here, the function itself, f of x, is decreasing. So it's probably no accident that the slope of the tangent line here is negative. Now over here, this tangent line touches this graph at approximately this point. And if you look at the original function at this point is increasing, so the slope of the tangent line you can see is positive. And this is no accident. There is a close relationship between the slope of the tangent line and whether the original function is increasing or decreasing. So tangents also give direction and motion, especially in a graph that models something that is in motion. So if you have an object in motion here, this tangent line right there indicates both direction, it gives the direction and motion of the object. So the slope of the tangent line is positive here, and it is going in a positive direction this way. Slope of the tangent line here is negative, and it is going in a negative direction this way. So I got distracted there for a bit. A ant crawled across my monitor while I was lecturing. So sorry about that. I had to pause the video and go deal with that. Anyway, so with slopes of the tangent lines, to find the instantaneous or instant rate of change, what you're going to actually be doing is finding the slope of the tangent line at that particular point. So the slopes of the tangent lines, as they are going to change along a curve. If you have a different point of tangency on the curve, the slope of the tangent line is going to be different. So these slopes of tangent lines, or instantaneous rates of change, are also called the derivative of the function. So instantaneous rate of change, slope of the tangent line, derivative, they all mean the exact same thing. And what we're going to do is there is actually a formula to find the slope of the tangent line, or to find the derivative of a function at a particular point. So this formula that I'm about to unveil allows you to find the slope of the tangent line at any point in the domain of a function on a function's curve. So we're just going to have a generic f of x here. I'm just going to have a visual. And we're going to have 2 points. Let's start with the slope of the secant line. So a secant line connects 2 distinct points on a curve. I'm going to call this first endpoint A, and its y-coordinate is going to be f of A. Now, instead of calling the other endpoint B, what I'm going to do is I'm going to call this other endpoint, its x-coordinate is going to be A plus H, where H is just however far apart the endpoints are. So H stands for the distance between the endpoints. And then the y-coordinate that goes with this would be f of A plus H. So the slope of the secant line would simply be the slope of the line that connects these 2 points. So the average rate of change will be the second y-coordinate, which is f of A plus H, minus the first y-coordinate, f of A, all divided by the second x-coordinate, A plus H, minus the first y-coordinate, minus the first x-coordinate, A. Then simplifying this a little bit, we have f of A plus H minus f of A. All over, those can cancel out, leaving you with an h in the denominator. Now, you might remember that the last time we talked about derivatives, which was the very first video lecture, we found our first derivative, our first instantaneous rate of change. Remember the rock problem? We found the instantaneous rate of change of the rock at 1 second by taking 2 distinct points in time and bringing them closer and closer together. So as these 2 points are brought closer and closer together, the secant line is going to eventually become the tangent line. Now, as these 2 endpoints are brought closer and closer together, what is happening to the distance h between them? Well, as the endpoints get closer and closer together, the distance h that's between the endpoints will get smaller and smaller and will approach 0. That should sound like a limit because it is. So if you then were to take this average rate of change and you were to take the limit as h approaches 0, what will happen was the two endpoints will get closer and closer together until the slope of the secant line becomes the slope of the tangent line. So it's basically the derivative is going to be the slope of the secant line where the distance between the endpoints h approaches 0. And this is what is called the limit definition of the derivative. So this is also just a nice, visual of what was happening there. So if you take the slope of the secant line, which is this formula right here, and you let the distance between the endpoints h go to 0, you have a situation like this. The one endpoint is brought to the other endpoint, and the distance between them goes to 0. And you can see by this visual that the secant line slowly becomes the tangent line as the endpoints get closer and closer together. So I did say a few slides ago that the slope of the tangent line is actually directly related to the behavior of the original function. So if you have a tangent line that has a positive slope, what that means is that the derivative is positive at this point A. And you will notice that the original function, which is this parabola-looking thing, is increasing at this point A. So the instantaneous rate of change at A is going to be some sort of positive value, and the slope of the tangent line here is positive. That indicates that the function itself is increasing. Now at this point over here, C, you can see that the slope of the tangent line is negative, which means that the derivatives are negative. This indicates a negative rate of change, and if you notice, the graph of the original function is decreasing at this point. Now over here at B, you can see that the slope of the tangent line is 0, which means that the derivative is equal to 0. And you can see that the graph itself is neither increasing nor decreasing at this point. This is what is called a maximum. Now, remember how I said that calculus was, primarily developed by two completely different people in two completely different parts of the world at the same time? Well, this is where that really becomes important. Because derivatives were developed by two different mathematicians, they each came up with their own very unique and very different notations for them. And because they have their own advantages and disadvantages, we actually do use both of them. So Newton's notation for the derivative looks something like this. This little apostrophe here is not a exponent of 1. This is read as f prime of x. The advantage to Newton's notation is that it is very simple and compact. And that's pretty much it. Now for Leibniz's notation, there's a couple different ways that you can write it. It is actually based on the slope formula, and what this means is you can read this in two different ways. This first one right here is read as the derivative of the function f of x, and the dx on the bottom is read as with respect to x. So you would read this as the derivative of f of x with respect to x. Now, you can technically put this f of x in the numerator, so you can also read this as the derivative of the function f with respect to x, or df dx for short. So it is read as the derivative of f with respect to x. Now a little bit more on Leibniz's notation. Again, this is the same thing. If your function is called y, then this is the derivative of y with respect to x. This notation is eventually going to be more useful because both the dependent and the independent variables are present, and it is clearly indicated what is the independent variable and what is the dependent variable. Remember, derivatives stand for something that is in motion, and they indicate direction and motion. So anything that is actively changing will be changing with respect to a single independent variable, such as time. And in a lot of scenarios, in a lot of real life scenarios, you have more than one variable that is all changing at the same time. So Leibniz's notation will help you keep track of which variables are dependent and what is the independent variable. So the independent variable, sorry, that is a typo. The independent variable is right here on the bottom. This indicates what your independent variable is, and you are always going to differentiate with respect to the independent variable. That means the dependent variable is here in the numerator. So since y is in the numerator and x is in the denominator, that means y depends on x, y is the dependent variable, and x is the independent variable. Now the d's here stand for what are called differentials. You have to remember that calculus was developed in stages by different people at very different times. So limits hadn't really been formalized when Leibniz was alive. So the concept was there. They were called infinitesimals at the time, but this limit notation right here, This didn't come around for until long after Leibniz was dead. So he didn't have this notation to represent this. So what he called these were infinitesimals. Infinitesimals represented a quantity that is forever decreasing in size. And so what he did was he let that phenomenon of the distance between the endpoints approaching zero, he called that a differential and notated it with d. So Leibniz's notation is actually based on the slope formula on which our limit definition as we know it today is also based on. Slope formula is the change in y coordinates divided by the change in x coordinates. Now, as the change in the x coordinates gets smaller and smaller, the delta x is going to become dx, a differential of x. It just stands for the x coordinates are getting closer and closer together. And as delta x becomes dx, delta y, the change in the y coordinates, becomes the derivative of y, which is dy. So we're going to do a couple of problems where we're going to use the limit definition. In the next video, in a couple videos from now, we're going to get into the derivative rules, which are shortcuts to finding the derivative function, which will make things a whole lot easier. But since this is a course objective, we do need to do at least a couple of problems with the limit definition. But going forward, once you guys see the video on derivative rules, you guys will be able to use the derivative rules going forward. So what we're going to do is we are going to find the equation of the line tangent to the graph of the function f of x equals x squared at the point x equals 1. So we're supposed to find the equation of a line, specifically the equation of the tangent line. Remember, what are the two things that you need to find the equation of a line? You need a point and you need a slope. So we're going to need the point of tangency. And we're going to need the slope of the tangent line. Well, we have part of a point and we have no slope of the tangent line. But let's get the rest of the coordinates of the point. So f of 1 is going to equal 1. So our point of tangency is 1, 1. So all we will need to write the equation of the line this time is to find the slope of the tangent line. Slope of the tangent line is also known as the derivative of the function at the point x equals 1. So that's what we're going to do. We're going to use the limit definition to find the slope of the tangent line of f of x equals x squared at x equals 1. So I'm going to use Newton's notation for this, and back here at the limit definition, this a here, a is the x coordinate of the point of tangency. So the point of tangency is 1, so the derivative at 1 is going to be the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. Now remember, with any limit, you need to do direct substitution. But so if you did direct substitution, you would get f of 1 minus f of 1, which is 0, over 0. So since this is a 0 over 0, that means we need to do a lot more work with this to simplify it. Now f of 1 plus h. We know what our f of x is. Our f of x is equal to x squared. So what I'm going to do is I'm going to plug 1 plus h with parentheses around it in for this x in our function x squared. So f of 1 plus h will be 1 plus h parentheses squared. Then minus, we already figured out what f of 1 is. F of 1 was 1. And again, if you did a direct substitution even mentally, you still get a 0 over 0, so we still have more work to do. So we're going to have to factor this eventually, because I did promise that all of these can be fixed by either factoring or rationalizing at this point in the course. So in order to factor this, what I'm going to need to do is I'm going to need to expand this 1 plus h squared, combine some like terms, and then let's try to refactor. So if you were to expand 1 plus h squared, you will actually get h squared plus 2h plus 1, and then we have that left over minus 1 all over h. Then the 1 minus 1 can cancel out. And if you notice, of the terms that are left over in the numerator, both of those terms have an h in them. So I'm actually going to factor an h out of the numerator. So I have h times h plus 2 all over h. So then h and h, there's that common factor that caused the 0 over 0, and those can cancel out, leaving you with the limit as h approaches 0 of h plus 2. And then after you simplify, we're going to direct substitute again, so we get 0 plus 2, which is equal to 2. Now remember, this 2 is the slope of the tangent line of f of x at x equals 1. So now we have the slope of the tangent line and we have the point of tangency. Let's put it all together into the equation of a line. So the equation of a line, you can go ahead and use point slope form if you want to. Y minus y1 equals m times x minus x1. So then y minus the y coordinate of the point of tangency, 1, equals m, the slope of the tangent line, 2, times x minus the x coordinate of the point of tangency, 1. And, you can go ahead and leave it like this if you want to. If you want to write this in slope-intercept form, all you have to do is distribute the 2 and add 1 to both sides to get y by itself. So you can see that using the limit definition to find derivatives is a lot of work, which is why we're not going to do too many of them. We're going to focus on using the derivative rules. Now, remember, the whole point in finding numeric derivatives is to find instantaneous rate of change and slopes of tangent lines. Now, in this case, this 2 here, because this function didn't really stand for anything in particular, the only way we would really interpret this 2 is just the slope of the tangent line at x equals 1. However, when your function does stand for something that is applied, that means you can interpret your derivative as the rate of change of whatever that function stands for with respect to the independent variable at a specific moment in time. So let's say that some function m of t, which I'm not going to give you, you don't need it. Let's say that some function m of t gives the body mass in grams of a baby owl at age t weeks. And I'm going ahead and telling you that m prime of 2 is approximately equal to 53.3. So what we're going to do is we're going to interpret this derivative in the context of the problem, and we're going to give appropriate units for this derivative. So this is the derivative of the body mass function at t equals 2. So at t equals 2, that means this baby owl is 2 weeks old. And this 53.3 is clearly a positive number. Remember that when the derivative is positive, that means the function itself is increasing. So since the function itself is increasing, that means the function m of t, which stands for body mass, is increasing. So the body mass is increasing because the derivative is a positive number. The derivative is a positive number, the slope of the tangent line is positive. So here's how we're going to interpret this. At 2 weeks old, the body mass of the owl is increasing at a rate of 53.3. And here's where the units are going to come in. Remember, the derivative is based on the slope formula. So the units are going to be whatever the units are for m of t per whatever the time units are. In this case, the units for the body mass was grams, and the time units was weeks. So at 2 weeks old, the body mass of the owl is increasing at a rate of 53.3 grams per week. So the derivatives are always going to have units that involve the word per something else. In this case, it's grams per week. Now remember, the slope of the tangent line on a function is going to be different at every point of tangency. So in the context of this problem, will this baby owl grow at the exact same rate at every single age throughout its entire babyhood? No, it probably won't. So because the baby owl is going to be growing at different rates at different times, if you were to evaluate the derivative at, let's say, 1 week, that derivative is going to be a lot different than the derivative at 2 weeks, because it's going to be growing at different rates from 1 week and 2 weeks. So always remember that a derivative is a rate of change. Now, we have what are called numeric derivatives, which is what we've been working with so far, and we have a derivative as a function. And they're both derivatives, but they're technically different. So derivatives that are calculated at a specific value of x are called numeric derivatives. This over here, this m prime of 2 equals 53.3, that is a numeric derivative. It is the exact slope of the tangent line at a given value of x. Now, a derivative function is a function that will give you the slope of the tangent line for any value of x that is within the function's domain. So a numeric derivative is a number that is a specific slope of a tangent line at a specific point in time, whereas the derivative function is a function that will give you the numeric derivative at any value of x that you plug in. So we're actually going to be focusing on finding derivative functions, because having a function that represents the derivative is really useful, because the slope of the tangent line is always changing as you look at different points of tangency along the curve. And you saw how much work it was to find the numeric derivative of a really simple function at a really simple point. If you have to find, let's say, the slopes of the tangent lines at several different points, you're not going to want to do that formula several times. You're going to want to do that formula once, get a derivative function, and then plug in whatever points you need to find however many slopes of tangent lines you need. Now, again, numeric derivatives are going to have slightly different notations depending on who developed it. So Newton's notation, we already saw with that m prime of 2. This is what Newton's notation means for the derivative of a function f of x evaluated at x equals a. So f prime of a means the derivative of f evaluated at x equals a. It's basically the same as function notation. Now for Leibniz's notation, remember df dx stands for the derivative of f with respect to x. This vertical bar right here means evaluated at. And it is evaluated at x equals a. Be prepared to use both. You will be responsible for both, and you will be using both. So what we're going to do is we are going to find the derivative function of y equals x squared. And we're going to use that derivative function to calculate the slopes of the tangent lines of x squared at x equals 0, x equals 1, x equals 2, and x equals 3. So instead of using the limit definition to find the numeric derivatives at 0, 1, 2, and 3, what we're going to do is we're going to use the limit definition once to find the derivative function, and then we're going to plug in each of these 4 points of tangency to get the slopes of the tangent line at all 4 of these points. So remember, our definition of the derivative looks something like this. The limit as h approaches 0 of f of, instead of using an a, I'm going to use a generic x, because we're supposed to find a derivative function, not a specific point. So it's going to be f of x plus h minus f of x all over h. And in this case, our f of x is equal to x squared. So I'm going to have the limit as h approaches 0 of, I'm going to plug x plus h with parentheses around it right there in for that x. So that will give me parentheses x plus h squared minus f of x, which is x squared, all over h. And if you were to direct substitute in for h, 0 in for h, you would get x squared minus x squared, which is 0 over 0. Remember, when you get a 0 over 0, you need to start thinking about rationalizing or factoring. In this case, we're going to be factoring. And in order to factor, I'm going to need to expand this and hopefully combine some like terms. So let's expand that x plus h squared. And that will give us x squared plus 2xh plus h squared. Then we've got that minus x squared all over h. Then x squared minus x squared can cancel each other out. And if you look in the numerator, there is an h in both of those terms. So I'm going to factor out a common factor of h. So that will give me h times 2xh plus h all over h. Then h and h can cancel each other out, leaving you with the limit as h approaches 0 of 2xh plus h. Now we're going to direct substitute. Now remember, when you're direct substituting, you're going to be direct substituting 0 in for h. So anything that is not an h can just be left alone. So that x right there can be left alone because it's not an h and it is not involved in this limit. So we're going to have, oops, sorry, that is a 2x. Sorry about that. So we have 2x plus 0 in for h gives us 2x. Sorry about that. So our derivative function, which I'm going to use Newton's notation, our derivative function f prime of x is going to equal x squared. Sorry, 2x. So our derivative function is going to be 2x. So what I'm going to do to find the slopes of the tangent lines at 0, 1, 2, and 3 is I am going to plug 0, 1, 2, and 3 one at a time in for my derivative function. So for my derivative function, f of x equals 2x. Let's start with 0. So f prime of 0 is going to be 2 times 0, which is 0. Then for f prime of 1, which we already calculated the long way using the limit definition, so f prime of 1 is going to be 2 times 1, which gives us 2. Same thing that we got last time. Then, finding the slope of the tangent line at 2, I'm going to plug 2 into my derivative function, so f prime of 2 is equal to 4. So what this means is that the function has a tangent line with a slope of 4 at x equals 2. And then plugging in 3, f prime of 3 is going to be 2 times 3, which is 6. So what this means is that x squared has a tangent line that has a slope of 6 at the point x equals 3. And again, we're not going to be doing that too much. We're going to be focusing on derivative rules. Now, before we get too far into derivatives, and even before we cover the derivative rules, we do need to talk about this concept called differentiability. So differentiable means able to find a derivative. So in order for a function to be differentiable at a point, all of these criteria need to be met. So in order to be differentiable, the function must be continuous at the point. If the function is not continuous, then it is automatically not differentiable. So in the previous video, we covered 3 criteria that need to be met in order for a function to be continuous at a point. So that means that all of the criteria for f of x to be continuous must hold in order for a function to be differentiable. And even further than that, the left-hand derivative needs to be equal to the right-hand derivative. It should sound like limits, like the limit on the left needs to equal the limit on the right, and it's because it is. Remember that the derivative is a special type of limit. So the left-hand derivative needs to equal the right-hand derivative in order for the derivative limit to exist. So this means that the slopes of the tangent lines on the left of a point must be the same as the slope of the tangent line to the right. As you get closer and closer from the left and the right, the two tangent lines need to start doing the same thing. So as you approach your point of tangency, the tangent lines on either side of that point of tangency need to start doing the exact same thing in order for the tangent line to exist at that point. So for the limit definition, the limit as h approaches 0 from the right of the derivative needs to equal the limit as h approaches 0 from the left. Points like this would fail condition 2. So this point right here in the middle is continuous. It meets all the continuity criteria, but it is not differentiable. Because if you notice, the slopes of the tangent lines on this side of the graph, so this line actually has a slope of -1. So on this side of the graph, the slopes of the tangent lines are going to be -1. However, on this side of x equals 0, the slope is 1. So the slopes of the tangent lines on either side of this point are not equal, and they're not doing the same thing, so the derivative does not exist at this point. No matter how close you get to this point, the two tangent lines are not going to start doing the same thing. They are not going to be approaching each other, so the derivative does not exist at this point. So here's another reason, here's another illustration of why those quote sharp points are not differentiable. You can see that at this corner point right here, L1 is the slopes of the tangent lines that are just slightly to the left. L2 is the tangent line just slightly to the right, and no matter how close you get to this point, these two lines always have very different slopes, and they will not start doing the same thing, and they will not start becoming the same tangent line. So there is no tangent line at this point. There is no derivative at this point. Here's an algebraic explanation of why those sharp points are not differentiable. We're going to use the example of the absolute value of x at x equals 0. Now, the absolute value of x is actually a piecewise function. It behaves like the linear function y equals x when x is greater than or equal to 0, and it behaves like the linear function y equals -x when x is less than 0. So for the right-hand derivative, that is going to be the absolute value of 0 plus h minus absolute value of 0 all over h, which, when you simplify that, gives you the limit as h approaches 0 from the right of the absolute value of h over h. Now, 0 from the right are values greater than 0, so you would direct substitute 0 into this top piece right here, which would give you h over h, which equals 1, and you get a slope of 1. Now, for the left-hand derivative, when x is less than 0, it behaves like the line y equals -x. So to the left of 0, the absolute value of h is going to behave like -h. -h divided by h simplifies to -1. So the limit as h approaches 0 from the left of -1 is equal to -1. So since the right and left-hand derivatives do not equal each other, that means that the derivative does not exist at x equals 0. So the limit as h approaches 0 overall will not exist. Now, a concept called local linearity is another demonstration of why sharp points are not differentiable. So we say that a function is locally linear at x equals a if the further that you zoom in on x equals a, the graph and its tangent line will become indistinguishable. So basically, in order for a function to be locally linear, as you zoom way in on the point x equals a, the graph should be indistinguishable from its tangent line. The graph should look exactly like its tangent line. That's what it means to be locally linear. So again, I can't do two things at once. If I try to open the graphing calculator software with this going, it will crash. So what I want you guys to do on your own time is I want you guys to graph y equals x squared, and I want you guys to zoom way in at x equals 1. We already found the slope of the tangent line of this function at x equals 1, and I want you to look at what this graph looks like zoomed way in at x equals 1. It should look like the equation of the line that we found a few examples ago. Now, with local linearity and sharp points, no matter how far you zoom in on this corner, will that corner ever go away? No, it won't. No matter how much you zoom in on that corner point, that sharp point will always be there. So it is not locally linear at that point 0, because as you zoom way in, it's still going to look like a corner, it's still not going to look like a line, and it's not locally linear. In order to be differentiable, a function needs to be locally linear at that point, so that is why the derivative does not exist at that point. So, For differentiability, the domain of a derivative f prime of x is going to be all of the values in the domain of x, of f of x, for which the derivative exists. Remember, sharp points are not differentiable. If a function is not continuous, it is automatically not differentiable. And another way that a function can fail to be differentiable is if it has a vertical tangent line. Remember, the derivative is the slope of the tangent line. What's the slope of a vertical line? The slope of a vertical line is undefined. So if your tangent line is vertical, that means your derivative is undefined. So we say that a function is differentiable on an interval a to b if the derivative exists for all x values between a and b. Now, there are going to be plenty of functions that are differentiable on its entire domain. So if the function does not have any points where it's not differentiable, then we say that it is differentiable on its entire domain. Now remember, being continuous depends on the being differentiable depends on the function being continuous. If the function is not continuous, then it is automatically not differentiable. Therefore, if you know that a function is differentiable, you automatically know that it is continuous. Now, there are going to be some points that are continuous but not differentiable. So the reverse of that statement's not true. Sharp points are continuous but not differentiable. But if a point is differentiable, then it is automatically continuous at that point. There is actually a theorem for this. If f is differentiable at x equals c, then you know that f is automatically continuous at x equals c. Please note that the converse or the opposite is not always true. Just because it's continuous does not mean it's differentiable. Think of sharp points. So, if you haven't really written anything down up until now, write this slide down. So, there are three different ways that a function can be not differentiable at a point x equals a. One, if it's not continuous at a. If it's not continuous, it's automatically not differentiable. Two, your function has a corner point or sharp point at x equals a. And three, if f has a vertical tangent at x equals a. So this graph here has a lot of problems. We're going to identify where this graph is not differentiable, and we're going to state why. So let's go from left to right. The first point that we find that is not differentiable is right there at x equals negative 5. Because at x equals negative 5, there is a sharp point. Next point where it's not differentiable is here at 4, again, because it is a corner point. Corner points are not differentiable. Then we have another one here at x equals negative 2. The reason why it is not differentiable at negative 2 is because it is not continuous at negative 2. If it is not continuous, it is not differentiable. And the reason that it is not continuous is because the limit does not exist. The limit from the left does not equal the limit from the right. Another point where it's not differentiable is here at 0, because there is a vertical tangent here at x equals 0. Another point where it's not differentiable is here at x equals 2, because the function is not continuous. If it is not continuous, it is automatically not differentiable, and it's not continuous because the limit as x approaches 2 does not exist. And those are this one illustration here pretty much gives all of the ways that a function can fail to be differentiable. So what I want you guys to do for this next one is I want you guys to take this function g of x. For part A, I want you to find all of the values on the of x in the open interval negative 4 to 4, so ignore the endpoints, for which the function is not continuous. Then for part B, I want you to find all of the values in that open interval for which g is not differentiable, and I want you to state why. So go ahead and pause the video and work through this problem. All right, so for part A here, where it is not continuous. Well, it's not continuous at x equals -2. Yes, f of -2 is defined, but the limit does not exist. Don't have a lot of room, so just limit does not exist. Another point where it's not continuous is right here at x equals 2 because f of 2 is undefined. Now, automatically, 2 points where this function is not differentiable are x equals -2 and x equals 2. The reason why 2 and -2 are not differentiable is because they are not continuous. If a function is not continuous, it is automatically not differentiable. And another point where this function is not differentiable is here at x equals 0. At x equals 0, it has one of those sharp points. You could also make the case that it is, it's looking pretty vertical at x equals 0. So if you argued that it's a vertical tangent, I'd take that too. I mean, you can make the argument. Whichever, there's a whole lot of reasons why x equals 0 is not differentiable. So that is going to be it for at least this section of differentiability. So this was just an introduction to derivatives, the limit definition of the derivative, and what it means for a function to be differentiable at a point. So in the next video, we're going to be going through the graphs of derivatives, and then after that, we're going to finally be looking into derivative rules. So thank you all very much for watching, and I will see you guys in the next video. Bye-bye.